Is it okay? That's the way?
Yes. Yes, now it's perfect.
Let's see now. Do what I should do there. The problem that, let's see, block my view. Let me see. Maybe I extend another window. See, put a different window. Okay, let's see. Yeah, okay. Maybe this is better. Yeah. Let's see. Hopefully working. Let's. Yeah, it looks like working. I cannot see you know, cannot see 1, 2, 3. I can see 6 people, 6 names. Yeah,
I think it's I think on one screen they will show you only just a small number of people, even though there are more attendants, in fact.
Yeah. Let's see. Let me adjust that. Interesting. Okay. Let me move back. Okay, let's see. Okay, I got it. Yeah, this is way better. Okay, this is Zoom, you know, it's a little bit adjust. So you use Zooms all the time or use Teams? We use Teams here.
I think in Korea, most people use Zoom.
Zoom, yeah. Yeah, Zoom more flexible, yeah. Okay. So this is 2 hours. Should we make a break or we don't have to do break?
So it's completely up to you. So if you think it's better to have some break in the middle, I think you can surely have some break time. So it's completely up to you. So there is no fixed policy about the lecture. So so we all leave all the powers to lecturer, not us.
Thank you. Yeah. So depend audience. Sometimes audience maybe 2 hours too long. They want to take up some break a little bit.
Sure. So the last time Figali gave a talk, and then he had a 1 hour lecture, and then around the 10 to 15 minute break, and another 1 hour lecture. I think that's how he did, and then it seemed okay.
Okay, so maybe I have 2 parts. Maybe I finish the part that started this asymmetric embedding. Maybe we could take a 10-minute break, something like that. Okay. Yeah. So I just you inform me. I just stop. Because
okay.
10 minutes. You're chairman, you know. You're this.
I'm a chairman, but we will see how it goes, and then we can make an adjustment in the middle anyway.
Yeah, after this year, maybe you check with me. Okay. And
okay.
For flu parts. Yeah.
So again, thank you for agreeing to give a lecture. You know, in spite of this big time difference, I know it can be very difficult for you.
Well, I made some effort. Yeah, it's better than last time I give a talk 4 a.m.
Oh, okay.
Yeah, time difference. Yeah. So that how everything you move to new place. Yeah, this. Yeah. So you're doing well. Everything.
Yes, yeah. I'm doing okay. I'm doing well.
Yeah. It's a good place. I like the city. I like the environment.
Yeah. I do too. So maybe next time when all this pandemic is over, you should come and visit sometime.
Oh yeah, sure. It's will be last time we enjoyed so much.
I see.
So we will have some meeting conference in Oxford, and maybe if I don't know whether you have time to come in. Yeah, we'll see. Yeah, I will send you something.
Okay.
Probably I think August. Yeah, I think August.
You mean
sometime.
this year? You mean this year?
So you cannot leave it probably, right? You cannot leave.
So the thing is, in Korea, the pandemic situation is still not that great. So many people are kind of hesitating to travel abroad. Although there are a lot of people, who really don't care and they just feel free to travel around. But especially for me, because I have a very little baby to take care of, so I'm not sure whether I will be able to fly around international this summer, but we will see.
Yeah. UK, we completely open up now, so it's normal. That's like before pandemic now, so everything normal, and we have to give a class, in person, everything.
I see. So then, so were you okay for whole time this pandemic situation in UK? So you did not have COVID, or did you?
No, I'm very fortunate now. I never had it.
Good. Because I heard that the situation in UK was really terrible at certain point. So
certain point. The most part of London area, and as a bigger city. But also the small size city better somehow overall. So now we open up people into pub to restaurant.
Oh, really? So you mean in indoor environment, you don't even need to wear any mask inside the building? Oh, really?
Yes, well, very high percentage of people here, they got 3 vaccines, so 3 shots vaccine. So they help a lot here. So we still have 1 minute, suppose, no?
Yes, because it seems that now many people are starting to enter, so we can just see. Yeah. Okay, so it's 4 o'clock, so maybe we can start now. So good afternoon, everybody, and good morning to Gui-Qiang from UK. So today I'm very glad that we have a wonderful special lecturer for our this wonderful Kaix Distinguished Lecture Series. So today, as you all know, so we do have this wonderful mathematician from UK, Oxford University, Gui-Qiang Chen. So before we start the lecture, let me briefly give an introduction about Professor Chen. So currently, he is a statutory professor in the analysis of partial differential equations and professorial fellow of Keble College in University of Oxford. And then also since the year of 2018 and until today, he is appointed as a director at Oxford Center for Nonlinear PDE in University of Oxford as well. And before he moved to UK, so he held his position at Northwestern University in US for many years. And in fact, that's when I got to know Professor Chen when I was a graduate student. And then also I was very honored to be his postdoc at a certain point for a very short time. But since then, we still maintain our relationship with wonderful collaborations in many research works. Okay, so let me also tell you a little bit about his background in his education. So he did his undergraduate in China, Fudan University, and then he received his PhD in the year of 1987, Chinese Academy of Sciences. And then his advisor is Professor Xia Ding. And then he came to US for his postdoc position. So he spent 2 years between the year of 1987 to 1989 at Korean Institute in NYU. And his mentor is Peter Lux. Actually, his research, he actually works on really various research fields, and among them, his main research area lies in nonlinear partial differential equations. And his recent research interest includes nonlinear hyperbolic system of conservation laws, nonlinear waves, nonlinear equation of mixed type, which will be the main topic of today's lecture, and free boundary problems and geometric problems and stochastic partial differential equations and so on. And he also had so many numerous honors and awards and fellowships, and among them, let me just list a few of them. So in the year of 2020, he's been elected as Fellow of the European Academy of Sciences, and in the year of 2017, he also was elected as a Fellow of the American Mathematical Society. And in 2014, he also was elected as Fellow of the Institute of Mathematics and its Applications. And in the year of 2013, he was elected as a Fellow of the SCIAP. And of course, other than that, he had so many wonderful honors and awards and fellowships. But it's already overwhelming to list all these. So maybe I will just start now. And then, of course, he has written so many great research papers, and then they were published in this prestigious journal that includes Annals of Mathematics, Invention, Journal of AMS and CPAM, so whatever you can imagine, he always publishes paper there. So it is really our great honor to have Professor Chen as the lecturer of today's Kaix Distinguished Lecture Series. So his the topic of the lecture is partial differential equations of mixed type, analysis, and applications. So even if we cannot just be in the same space at the same time, please show your welcome by pressing the hand button to welcome Professor Chen. So, okay, so please, now it's your time.
Oh, thank you very much, Gui-Qiang, for your kind introduction. I feel actually overwhelmed. So it's really my great pleasure and honor to be invited to join all of you and to give this talk in your distinguished lecture series today. I would like to thank the organizing committee for the invitation. So as Gui-Qiang introduced, the topic of my talk is on the analysis and applications of partial differential equation of mixed type. Basically, I'm going to present some older and new underlying connections between partial differential equation of mixed type and several fundamental problems in fluid dynamics and differential geometry and other areas. And to discuss some recent developments in analyzing and solve those mixed type problem with application through this those connections. Let me start with some background. Well, as we well know, the three of the basic type of partial differential equations are hyperbolic type, elliptic type, parabolic type, following the classification first introduced by Jacques Adama actually in 1923 in his book and around the 1920s. The prototype of hyperbolic equation is the wave equations, or some related Maxwell equations, which take the form here. This form describe the propagation of waves such as acoustic wave, electromagnetic wave, and many other linear waves. The simplest representative of the second order elliptic equation is Laplace equations, or sometimes called also equilibrium equations. Describe the physical equilibrium states. We often describe physical equilibrium states whose solutions are called harmonic functions or potential functions, while the representative of a parabolic equation is a heat equation, describes the dynamics of temperature and various the diffusion and stochastic process. So those three equations, at the first glances, right? Those three equations looks quite similar. All involve the second order derivatives terms, homogeneous derivative terms. Especially the solution of elliptic Laplace equation is a steady state solution of the wave equation and the heat equation. And those solutions also could be regarded as the asymptotic state or equilibrium state of the solution of the parabolic, the heat equation and the wave equations. However, the behavioral solution is very different, as we learned from typical the first class of the PDE courses, right? One of them is the finite versus infinite speed of propagation of solutions. The another is the gain and loss of regularity of solutions. On the other hand, the wave Laplace equation and parabolic, they have a common feature, very many common features. So this talk I will focus on the partial differential equation of mixed elliptic and hyperbolics. Although the other equations are mixed parabolic and hyperbolic equations as well. So now the classification can be seen more clearly for the two-dimensional constant coefficient second order PDE, which take the form, this form. Now the coefficient Aij are constant. So you can form 2x2 symmetric matrices. Then 2x2 symmetric, you have two layer eigenvalues. Then this second order PDE we call is elliptic if this matrix is positive definite. Corresponding to eigenvalues the same sign. Okay. Otherwise, we call this equation hyperbolic. Okay, typically two eigenvalues negative different signs. So this classification is just like what we classify the conic section on quadratic form in algebra geometry. Depend the discriminant. Based on discriminant, I wrote down A1/2 square minus Aij, A11, A22, the sign for that. So they divided this conic section and the quadratic form as a similar hyperbolic, parabolic, elliptic. Corresponding quadratic curve are parabola, ellipses, hyperbolas. Okay, so this classification also can see more clearly through Fourier transformation. If you take a Fourier transform both sides, then you got now coefficients Aij, this exact quadratic form. We talk about algebra curve. Then you Fourier transforms you have your solution and equal to right hand side, right? Then now if the elliptic, right? So this means this is a discriminant less than 0. Then this never equals 0. You divide the quadratic form to right hand side. You find the Fourier transform of solution. You gain two orders for high frequency, Fourier high frequency for that. So you gain two order regularity. Now for hyperbolic case, this quadratic form degenerates along the characteristic directions. So your solution will be lost regularity in certain direction. We got wave cone around the characteristic direction. Away from wave cone, of course, still you gain regularity for that. Okay, so this is the close connection with the PDE classification, whereas classification or algebra quadratic equations in algebra geometry. Now, another thing very important, when this equation elliptic, the discriminant less than 0, you can make a coordinate transformation. This general second order equation, constant coefficient, you can transform to exactly Laplace equation. The same, if the discriminant bigger than 0, slow coordinate transform, you change it to wave equation. So this is expose the beauty of this classification for the constant coefficient second order case. Now for variable coefficient case, situation more delicate. Okay, so in this case now, coefficient ai, j are no longer constant, they are functions. This coefficient matrix still 2 by 2, symmetry, you have 2 eigenvalues. So generically, these 2 eigenvalues may change sign, slow from one domain to other, one part region to other part domain. Okay, one domain and the other domain for that, different places. So here is, I give you the 3 fundamental examples. Okay, typical like the first equation example, the coefficient change sign, right? Sine function, discontinuous jump, sine function, simple function. The second equation, Jacobi equation. Then so that when chaotic equation, the coefficients they are also very nice, okay? But they really represent a different type of degeneracy. Okay. More precisely, the first example, the sine function, you will see if u bigger than 0 in the half plane, right? So the equations become exact Laplace equation, or x less than 0 wave equation. Then transition boundary x equals 0. Slow the jump discontinuity coefficient sign is sine function for that. Okay, so this is a mixed type from elliptic hyperbolic. Slow the transition boundary x equals 0 from basically Laplace equation to wave equation. The jump slow x equals 0. Okay. Now Jacobi equation is different. Now coefficients are continuous. Then of course u bigger than 0 the elliptic equation, u less than x bigger than 0 elliptic equation, x less than the hyperbolic equation. So this equation of course is of the hyperbolic degeneracy at x equals 0. Reason is you compute 2 characteristics when x equals less than 0. The co-characteristics coincide when the touch to x equals 0, but perpendicular, okay, to the but they becomes original hyperbolic equation become degenerate hyperbolic equation. 2 characteristics coincide, but perpendicular to the degenerate curve. The transition boundary. Okay. Now you look coordinate transformation. You could transfer Jacobi equation as now we call elliptic hyperbolic Euler-Poisson double equation, which is you have an operator like Laplace operator and the wave operator. Then the single first order term, the singularity. The sign, the coefficient beta is essential. Okay. Represent the degeneracy or the kind of degeneracy. Roughly speaking, actually beta bigger than 0 hyperbolic degeneracy. Okay, later with that. Now, in contrast, the chaotic equation is different. Okay, although this x in this direction, then still of course mixed type from elliptic to hyperbolic slow x equals 0. But degeneracy, the equation has a parabolic degeneracy at x equals 0. Difference, the 2 characteristics family, they are quadratically parabolas lying on half plane, touch tangential at the contact points to the degenerate line. Okay, the tangentially the characteristics for that. So you could do the same slow coordinate transformation. You can get this again the elliptic elliptic hyperbolic or Poisson double equations. Difference between Kaix Jacobi equation beta sign change. Beta from 1/3 now changing minus 1/4. Is one is positive constant, one negative. They give different type of degeneracy near the x equals 0 or tau equals 0 related with that. Okay. Now for those kind of PDE, for those kind of PDE now, the common feature, of course, that the transition boundary x equals 0. All right. That means you know the boundary of the type change from elliptic to hyperbolic for such PDE for that. The boundary between elliptic domain and hyperbolic domain, is a priori no for that. Okay, so one approach of kind of to handle those kind of linear PD of mixed type, you divide the problem to different region, elliptic domain, different domain, right? Elliptic domain, hyperbolic domain. You understand the behavior of solution in the elliptic side as the general elliptic, like here, elliptic Poisson double equation. Then hyperbolic, you understand the behavior of solution, hyperbolic Poisson double equation. Then you put together, you try to understand the behavior solution of mixed elliptic hyperbolic partial differential equation. Another approach, traditional approach, is called fundamental solution approach. You globally found the fundamental solution. You are trying to understand the behavior of fundamental solution. Then you understand the solution behavior near the transition boundary, special transition boundary. Since the fundamental solution is a generator of general solution of linear partial differential equation. Correct. Okay. So today I want to present a different perspective that through several examples, many nonlinear partial differential equation actually are arising in the many different areas, especially in fluid mechanics and differential geometry and other areas. They are not single standard type. They are, but very often a mixed type. Okay, very often mixed elliptic hyperbolic type. Okay. So solution of those through the several fundamental problems here. So solution of those fundamental problems require deeper understanding of the nonlinear PD of mixed elliptic and hyperbolic type. Okay. Now for nonlinear case, of course, the coefficient ARG not only depend x, y, also depend u, sometimes depend ux, gradient of u. So before you solve problem, of course, you don't know, different from linear case, you don't know transition boundary. You don't know where the elliptic will have the hyperbolic until you solve the problem. Then you do go to estimate. Then you see, you will find, oh, this equation, the elliptic in certain region, domains, a certain domain hyperbolic. Okay. Then actually transition boundary is a free boundary, okay, between elliptic and the hyperbolic. Okay. So since this is the complication, the many very powerful and useful the methods approach in the theory of partial differential equation, linear partial differential equation, they are no longer applicable to those PDEs. Okay, so the require really new ideas and techniques and approach, new mathematics. Okay, so deserve our special attention. So now I'm trying to give you the several class of examples of such nonlinear partial differential equation of mixed elliptic hyperbolic. The first class of those nonlinear PD of mixed type from the shock wave problems. Okay, so shock wave occur in many different physical situations. For example, we could observe a very strong shock, we now call ball shock, between Earth and the Sun very often during the Sun explosion. So in the Sun explosion, the Sun emits ionized gas in one direction, form like a piston problem. Then you form a very big shock in space between the Sun and the Earth. So this is really good shock and to protect us from someone laying or sun, the explosion, okay, for protect our Earth. So this kind of shock could generate in the from a surface explosion. During the surface explosion, you form the first form fireball, then form the almost flux-match shocks outside the ball here. Okay, it's propagate to go this direction. Okay, so after cross shock, the density, velocity, and temperature express the jump, slow the shock. Shock really could dimension one surface basically for that. So those kind of shock also can be generated by supersonic aircraft. So I took the example, this is from F-18, this is now more recent to F-38 actually, T-38, yeah. So this is a new one, the actual experimental NASA March 5 in 99, yeah. So this is here the two supersonic jets, right? They try to experiment, trying to really want to understand the interaction of waves. As you can see now, this is amazingly experiments. Okay, I would point the two pilots, both are female pilots. Okay, they did this experiments very successfully, but very high challenging experiments. But you will find now this is the shock formed in front of supersonic jets. Then depend geometry of jets, you generate the other shocks from other places. Okay, so you can see when if the speed becomes faster, the shock wave becomes strong and strong. So more close look now is this is a shock wave generated by the sharp-nose supersonic model in wind tunnel. You can close look. Here you will find this is a two-dimensional model. Then you will find in the front the shocks formed. Then the shock formed is the corner from this wing here, strong shocks. Okay, so the other place there's shocks for that. So the first example is actually the following shock shockwave problem. I want to as example is called the supersonic flop pass on the solid wedge. Okay, so set up very simple. This two-dimensional wedge. The supersonic from far field. Then, interesting, you'll find there are two solutions. One solution called strong shock, always a supersonic, transonic shock we call. The supersonic to subsonic. Another shock, weak shock, depend wedge angle. If wedge angle is less than that, will be the supersonic. Then if wedge angle beyond the sonic, then you still become transonic, supersonic, subsonic. Okay. Now in terms of PD language, this is called transonic means one side is hyperbolic, the other side elliptic. Okay. But now then you will find the two solutions. You give a PDE full dynamic PD, I will explain later on. Then you solve the problem, then satisfy the entropy condition called Siegel-Law thermodynamics. Then you find two solutions. So it's a surprise, a so simple problem. You get two solutions very naturally. You cannot exclude one of us. Okay, so this is related with now somehow related with the non-uniqueness issue, right? if the question whether both of shock are admissible, if admissible, how could we understand non-uniqueness issue? Then if not, then how could we exclude one from the others? So this got attention from the early days by the Planto. So he examined many experimental results. Then he conjectured the wake shock is a physical admissible, since all experimental results show that by that time always pick a wake shock solution. And he also later on formed the configuration. He conjectured now we call Planto-Mayer shock configurations. And dynamically, he thinks this solution configuration dynamic, it goes infinitive, will tend to the wake shock solution asymptotically. Okay, from steady state problem to dynamic problem to steady state problem. So this is the caught the attention when Coulomb Friede they looked at this project, book project around 1940s. Now is a monumental book called Supersonic Flow and Shock Wave. And during that period, they document all the possible experimental results they got, and they systematically analyze this problem carefully. And they actually, in this book, you find the two long sections contribute to this problem and the related topic. Then in the book, I just quote now, so they point out the question arises which of the two actually occurs. It has frequently been stated that the strong one is unstable, and that therefore only the weak one could occur. A convincing proof of this instability has apparently never been given. Okay, so this is the conclusion. So somehow they agree with Planto. Should the weak shock solution that could occur, okay, but no proof of that. Now this is again, this caught the attention of von Neumann actually after that. So in the von Neumann, he formulated a panel discussion during the joint international conference of the International Union of Theoretical Applied Mechanics and the International Astrophysics Union. He formed this panel discussion. So he invited the prominent scientists of that day, including Burgers, Hessenberg, Lippmann, von Karman, and others. And the topic they discussed on the existing uniqueness and multiplicity of solutions of the aerodynamic equations. And he opens this panel discussion, and he started the talk. Started the statement as following. The point first he started, wow, this is the problem. Simplest hydrodynamic problem have several solutions, some of which are very difficult to exclude on mathematical ground only. Okay, so he examples what exactly are described now. There are two solutions: like supersonic flow of gas, like concave corner. Okay, which obviously leads to the apparent shock waves. In general, there are two different solutions with shock wave. It is perfectly well known from experimentation that only one of the two wake shocks occur in nature. But I think he pointed out his point. All stability argument to prove that it must be so of very dubious quality. So he was not very optimistic whether we could claim up this problem through mathematical analysis, stability analysis. Okay. So the actually about 20 years ago, we started this this project research there. We saw that after the more than 50 years since in 1949, there would be much theoretical progress on this problem about the non-uniqueness issue. And to our surprise, there would not be actually significant theoretical results, especially in terms of the mathematical stability argument as von Neumann wanted. So we started the problem trying to understand this problem through the static analysis to see whether we could understand the non-unique issue through perturbation incoming flow, through proflow and perturb wedges. Okay. Now, so this is a step. The first example that we consider the steady Euler equation for potential flow. And then static Euler equation for potential consists of conservation mass, then the Bernoulli law. If you represent the now gamma constant, okay, some power. So if you represent the density in terms of gradient phi, plug in the density into the first equation, you call the second order nonlinear PDE for phi velocity potential. Okay. This is second order P. Now, if those of you maybe some special graduate student Schrödinger-Gilbert book in second order elliptic equation, we look, wow, this is really like second order elliptic equation. But turns out this equation not only elliptic, but sometimes also hyperbolic. So this equation is really a nonlinear conservation law of mixed elliptic hyperbolic type. So this equation is elliptic, second order elliptic, when gradient phi less than C star, then constant. Okay, otherwise hyperbolic. The transition boundary is really restriction of gradient phi of solution equal constant. That curve that generally set the form degenerate of equation, which is a priori unknown determined by solution, like a free boundary for that. So before you solve the problem, you really don't know this equation is elliptic hyperbolic, where elliptic, where hyperbolic. Until you solve the problem or get a gradient estimate, then you can identify the lead domain where equation elliptic, where hyperbolic, or solve the free boundary problem for that. Now, this I give you Euler equation for potential flow. Then for Euler equation for four Euler equation, then we're coupling with other equations. Then the whole system will more complex, form mixed composite elliptic hyperbolic type. Okay, so with those kind of PD, then through the effort of the last 20 years, the stability of two steady shock under steady perturbation of income flow and the wedge boundary has been much better understood so far. For weak supersonic shock or weak transonic shock, we can prove now through our work and other research. Now we can prove that they are always stable. Okay, in perturb incoming flow, perturb the wedge boundary, the weak supersonic shock solution, weak transonic shock, they are all stable. Okay, so this verifies the conjecture by Planto and Coulomb-Friedrich. Now, in terms of von Neumann, we rigorously prove in this steady framework, this can be confirmed. They're really stable. Now, for short transfer are very different. We still can prove stability, but under conditional smooth perturbation. You could not prove stability for any perturbation. The perturbation, you have the restriction, especially the downstream at infinity, you have to need the restriction, not arbitrary. Should set of certain conditions, then this shock is stable. Generic, it's not stable. Okay, so this is the reason why experimental results somehow very difficult to observe because you set up experiment not so easy to match this conditional condition downstream and generically. Mathematically, we can really understand now very clearly to give the criteria, what kind of condition that make this perturbation class stable and generic and not stable. So this is more of when we further understanding of this stability issue of the weak and strong transonic shocks and the steady framework. Okay, so this kind of analysis is also generate multidimensional game. So our problem, of course, for weak strong involve nonlinear PD mixed elliptic and hyperbolic. Okay, so next one now. What about the unstable case? Can we show asymptotically solution asymptotic goes to the, for example, one of them weak shock solution or strong shock solutions. It turns out that this problem also can be reduced to the nonlinear PD of mixed elliptic and hyperbolic. Okay. So let me explain a little bit more briefly about that. So now the question, this is the experimental, that is numerical result. So basically, dynamically, start initial data is a flow moving from far field to the two-dimensional wedge. Then you get a shock coming out. Then another part of the normal effect shock, they form this kind of configurations. From numerical experiment, this is a transonic shocks. Outside of this coming flow, inside the flow kind of complicated, but some part elliptic, some part hyperbolic, suppose. Then the outside the hyperbolic, okay, there's a transonic shock from that. There are two configurations, basically. There's a wedge angle if it's called sonic angle. If wedge angle is less than sonic angle, so state behind the attached shock tip of subsonic, there at the beginning, there's the neighborhood of the corner, that's weak shock, then the subsonic region. Then another, if the angle between sonic and detachment, then immediate from shock, then immediate becomes the subsonic elliptic. Okay, there are two configurations, actually two cases. The question, can we prove such configuration exists? And can we construct solution that? Then we prove weak shock. If we take a corner weak shock is a physical admissible. Okay, so this problem really, then you may ask, this is so concrete the problem, why so many scientists care about this? Actually, there are more deeper insight for our mathematicians, because this kind of configuration is one of the prototypes for solution of two-dimensional Riemann problem for hyperbolic conservation law. If we could start the, we have solution first order system, okay, then our second order equations depend the conservation forms, hyperbolic, then nonlinear wave equation for them here, this hyperbolic conservation law. Then Riemann solution. Riemann problem means that it was actually first studied, introduced by Riemann for one dimension case, with this two constant state initially with jump through the one jump, okay? Then you see how to find the global solutions. This is a two-dimensional version of Riemann problem. You mean special class of initial data such that initial data only depend angle. For example, piecewise constant, the sectional constant here like that, okay? So it's very easy. The previous configuration I show you, you can prepare the initial data. As initial data with boundary, with self-similar structure, then you construct a solution like that. Prepare those data, then solution becomes that. So this Riemann solution actually has solutions have played very important role in mathematical theory of conservation law, especially determine local structure and the building block of general solutions on entropy solutions, also determine asymptotic state, a check of general entropy solutions of the hyperbolic conservation law. Okay, so in order to understand the solution structure of the general entropy solution, we have to understand this kind of configuration of solution for that. Okay, so now the problem now, original problem, now the time-dependent problem. I come back now. I focus now for simplicity. I focus on Euler equation for potential flow. So now velocity, phi the velocity potential, can write this form. Then first equation, the conservation mass. Again, second equation now Bernoulli law, the time-dependent here. Again, I can, the gamma is any constant. Okay, gamma minus rho. I can represent the density in terms phi t or greater than phi, then plugging phi into first equation, form the nonlinear wave equation, seeking out the nonlinear wave equation. Actually, this is one of the early motivations why we, so interesting study nonlinear wave equations in mathematics, and so. Actually, the Adama, he shows that if initially initial data the co-zero with potential more than irrotational, then you can put if solution reasonable regularity, then solution keep the same form, okay, or cross some boundary like that. So. This is the equation I want to now to focus on to show you how this is really hyperbolic PDE. Okay, so I want to show you how come out through this problem, how nonlinear PDE or mixed elliptic hyperbolic type PDE arising from this problem. Okay, so this is because this problem you can formulate initial boundary problem. Basically, your incoming flow you have initial data. Okay. Then slip boundary condition because the boundary is solid boundary, and so whole problem I showed you earlier, the Plato-Meyer configuration is really initial boundary value problem for nonlinear wave equation set up like that. So now if you look at the problem carefully, you find the problem is invariant under self-similar scaling. Means you Tx, you put alpha T alpha X, and the low phi, you take a low phi divided alpha any alpha, then nonlinear wave equation is invariant. Initial data is invariant. The boundary condition is invariant. Okay. Now from experimental result, you can see the solution really is self-similar type. Okay. So naturally, we're looking for solution constructed the Plato-Meyer configurations. We're looking for self-similar solution. So self-similar solution means you're looking for solution only depend cosine eta, which formula x1 divided t, x2 divided t. Then density depend cosine eta, this form, velocity potential, this form. For convenient, I take the quadratic form out. Then focus on this phi. Then what do you find in the calculation? Phi was set against that phi, seeking out the nonlinear PDE. Okay. Different from static case is static case we don't have two low term. You have to independent phi the low density. Now the more complicated. The equation density function depend now the not only gradient phi, also phi. You can represent this form. Okay. So this is a really nonlinear equation, a mixed elliptic and hyperbolic. Again, when this equation is elliptic when gradient phi less than c star, before the constant static is now depend phi. Then otherwise the hyperbolic is straight hyperbolic. Generically, you automatically get seeking out the nonlinear PDE of mixed elliptic and hyperbolic type. Okay. So before you solve this problem, we really don't know where's the elliptic, where's the hyperbolic, if you talk about the physical domain. Until we solve the problem, we understand free boundary, or we estimate the gradient estimate of a solution, then we know the PD, whether this PD, where the PD, this PD elliptic were hyperbolic. Before solve the problem, we really don't know for that. So this is an example I try to show you, the very naturally arising non-PD of mixed elliptic hyperbolic. Although the original problem, the hyperbolic, now you reduce to mixed type. The whole problem, of course, the become now on the self-similar quantity, original initial boundary value problem become boundary value problem in unbounded domain. Slip boundary and self-similar quantity the same. Original initial condition become asymptotic boundary condition. It means that at infinity, this all solution should matching this incoming flow. Okay, it turned out you can through the hyperbolic, hyperbolic theorem, we can prove that the solution from infinite case outside, you can put a constant. There are two shocks. One shock from the origin, we take a weak shock. You want to prove Plato-Meyer configuration, Plato conjecture. The solution asymptotically go to weak solution. So we choose a weak shock. Then other part of the follow with your shock, you form the norm shock, okay, reflex shock basically. So these two shocks can be determined by hyperbolic theorem. You can find the location of a Sn, you find the state of omega n, you find the slope of the shock and the state omega zero state. Okay, then the whole problem reduce the local problem. Then after we solve hyperbolic problem, verify hyperbolic outside the state theorem, hyperbolic theorem. The inside really want to see whether we can, this two boundary can determine. The whole part really we can determine shock, the connectors from here to here through shock, and inside is elliptic, outside hyperbolic. So that is the whole problem that eventually deals that. Now, I have talked so many times about shock wave. Let me explain a little what is shock waves. Shock wave really link your whole conditions. So the following, shock wave really could dimension surface connect the two states, okay, from left to right? So it's supposed to continue both sides, and then the jump across the codimension surface, we call ACE. Then we want both sides solution, classical solution, then jump through codimension one surface. Then you want to put the two solutions together through this codimension one surface. We want to become weak solution of original nonlinear PDE. Then necessary sufficient condition is Qiang-Hugel conditions, basically two conditions in terms of the likelihood for potential flow. One is phi continues through, phi itself continues through the shock, but then imply tangential derivative continues, but normal derivative jump, okay, slow this relation, okay, this algebra relation. Okay. So it means that for physicists, they call Qiang-Hugel condition. For more mathematician, we want really piecewise solution connected by codimension one surface. You want to put the piecewise to become global solution, weak solution of PDE. Then necessary sufficient condition by integration by parts, you need the two conditions. This is an algebra condition. Okay, so this is a requirement of a shock wave. Then the second requirement for entropy condition. In this case, this equivalent to second law thermodynamics. The equivalent to the discontinuous function rho increase across shock in the pursuit of velocity. Then if satisfy the two Qiang-Hugel condition and entropy condition, we call this shock waves. Okay, so through shock you have this jump conditions. So this is what I construct. These two shocks here. They closed two state outside hyperbolic is both hyperbolic satisfying conditions. Here, hyperbolic have also satisfying conditions, two conditions here. The question we want to find another shock, transonic shock, outside hyperbolic is inside elliptic, but should satisfy two conditions there. Okay. Another interesting state called constant state. If the density constant, then because I shift the quadratic, now this potential, pseudo potential, with now also linear, then plus quadratic form. Then now in the cosine eta plane, for constant coefficient, the constant state solution, there's a cosonic arc, circle or arc. Okay, because it's quadratic here. So you're given state, okay, U0, V0 constant state. Then this with center in the cosine. Then with the radius C0, this cosonic speed. Okay, so there's circle or with like a state here, in state, the center something here. So there's circle here. Inside the circle, this equation is elliptic, outside the hyperbolic. Okay, but even constant state there, yeah, you're given constant, you can determine circle. So this is called sonic circle for state in, this sonic circle state 0. So it can be determined now. So whole problem now outside we all determined through the hyperbolic theorem. The question how to find a solution inside, which involves the free bond, the problem mixed elliptic and hyperbolic problem. Okay, so this problem formulated as free boundary problem for mixed type PDEs. Basically, you want to find a solution, curve the solution here, this one, okay? Outside the hyperbolic, inside the elliptic, hopefully, okay? The satisfy equation both sides. That's now this under this shore, they call free boundary set of two conditions, okay? Then, now, on the other hand, the sonic degeneracy curves, this degenerated, now this is not a shock wave, but still your two solutions, if we find a solution inside, outside, put together, you want to satisfy PDE, your slow, weak solution, still there are two conditions on these curves because our coefficient of equation depend grading of phi. So you have to satisfy two conditions, both sides. Now, traditionally, of course, if inside the elliptic, free boundary two conditions is fine. Now, the fixed boundary here too, we only could give one condition, right? The deletion boundary problem for elliptic. Now, physical problem, we want to match two conditions. So, on the other hand, this boundary is degenerate elliptic if we're inside elliptic. Then hopefully degeneracy help us to match another condition eventually. Okay, then the boundary condition. So this is the whole problem, the free boundary we want to solve here. So whole thing, we question whether we do such solution exist globally in general, especially for all region of parameter of potential from when theta less than sonic angle and beyond sonic angle. Then what about optimal regularity for this free band, through these free boundary problems? Okay. So there are several mathematical challenges here. One of course I mentioned earlier, non-linear mixed elliptic hyperbolic type. The transition boundary between elliptic and hyperbolic phase a priori unknown, right? The second way, those free boundary actually could not formulate the variational form. Okay, we don't know how to do that. Yeah, the problem cannot, but the question whether, yeah, they are very power taking a variation approach to handle free boundary problem. So we could not directly apply those approach here. So need a new approach for this free boundary problem. Then what about optimal estimate of solution to nonlinear degenerate elliptic near the like two sonic circle and also free boundary intersect with the fixed the degenerate boundary. What the optimal regularity here, the corner regularity here. Okay, the one thing of course to match two boundary conditions and the corner regularity. Normally, the standard theorem elliptic, you study corner regularity, you normally assume nonlinear PDE with closed conditions. Unfortunately, all this PDE, this physical PDE here is without those conditions. So, so this kind of corner link singularity we had to examine, see whether still could get a similar result without the closed conditions. Then another problem, of course, geometric property of free boundary, whether convex, all those transversal, and so forth. So here's the result. We with Mianjiang and Michu, now accept the memoir of American Math Society. We prove that the answer is yes, we can get a global solution and optimal regularity of the weak shock solution up to sonic angle. And the shock, the two straight shock connected by this now curved shock. Okay, slope not match the slope, also curvature match. And the closest this two fixed degenerate boundary, the two condition match, and even C11 solution. And we can prove solution C11 the corner when free boundary, the corner met this fixed degenerate elliptic boundary as C11. Okay. Those kind of estimate optimal, and we get various property about solution monotonicity problem and so forth. Okay, so this can solve this kind of problem, free boundary problem mixed type PDE. And then what about beyond angle? The answer yes, we also can get it. For this case, now home region, now no hyperbolic region here, or elliptic region. This hyperbolic degeneracy from here, and the free boundary start from corner to connect with the normal effect shock, the C11, and then optimal regularity as well. Okay. So this approach and the related techniques has been developed really based on the ideal technique from our early related work. Without built up our early work on the shock reflection deflection problem, then based on those early work, then we further developed the ideas techniques to solve the problem here. So this is a book published 4 years ago with Feldman. This talk about another problem called shock, mathematical shock deflection, and the non-linear conjectures. The solve other the shock wave problem for mixed non-linear equation of mixed elliptic type. Okay, so the basic I just quickly procedures use the free boundary procedures iteration procedure. We solve the very important the first four, those are a priori estimate. You first get a strict monotonicity property estimate, then uniforms. Then you want to elliptic region the boundary, not go infinitive. So in the C01 estimate of this inside this omega domain, how big is this omega domain? Then the C11 first Lipschitz, this free boundary first pro Lipschitz, then the phi related to phi with respect to a wedge angle. You know, this how depend the wedge angle and the uniform estimate of ellipticity, then the weighted estimate, uniform estimate for solution, C2 alpha inside. So those are very technical and need the a priori estimate. Okay, so this estimate it takes more than 100 pages for that. Now with those estimates, then we define iteration set and the iteration map, then set up as the fixed point setup. Then eventually we use the degree theorem, Lalish short degree theorem, proves there's a fixed point for solution for all wedge angle up to the detachment, sonic angle and detachment angle. So whole part of that first 4 step, the uniform a priori estimate to get that. Okay. So then question, what about the now previous result, we proved that the global weak Planck-Meyer reflection configuration exists to that. So what about strong Planck-Meyer reflection configurations, whether they exist or not? It turned out that you can use elliptic theorem to exclude that for no existence for strong plane-to-mirror reflection configuration. Difference is the corner conditions here. This is like elliptical problem here. You have a corner. For weak shock, this condition, the oblique boundary condition, the normal in this direction. So allow you pick additional elliptical condition problem in the corner. You allow you put another data, value, okay, another condition at the corner. This is what we did, match to the condition inside the phi from outside phi, given one more condition you can prove globally. Now for strong shock case, the normal oblique normal conditions will not allow you to freedom to choose another data here, but then you use the APR, the maximum principle argument. You can prove this impossible to find a solution in genetic. If you add the continuity conditions to outside inside, then you cannot find solution. So this is now provide another understanding for Pareto conjecture, whether you dynamically the strong shock, we prove that weak strong shock solution to the asymptotic state of the time-dependent plane-to-mirror reflection configuration solutions. For strong one is not. Okay, so this is the way. So now listen to the way. Now the study those short, trans-short, weather convex geometric property of it. And we developed the new approach to handle the free boundary, convexity of free boundary. Then we prove that actually all those transonic shocks in this shock problems, reflection differential problem, are uniform convex, except some ending points. Away from ending points is uniform convex. Okay, those free boundary, the shock with free boundary. Now, based on this observation, we now prove that the uniqueness stability of global shock reflection differential configuration with respect to wedge angle. This is a prevalent still, yeah. We still try to improve that maybe in the next few months. Okay, so there's prevalent there for that. So this so far I now focus on the example, the Euler equation for potential flow. Really show you there are several of those canonical PDE coming out from the naturally from fluid dynamics, which are thinking of the nonlinear PDE of mixed elliptic. Related problems are the mixed type problems. Now, in some time, the vorticity becomes, that's for vorticity small case in the flow. Then sometimes vorticity become significant. Then we actually come to the four Euler equations. Then for four Euler equations, then conservation momentum, mass, momentum, and energy. Okay. Then you use self-similar coordinate. You will get this Euler equation form, the four Euler equation form this form. Cosine 1 cosine to this form, then the lower coupled with the lower order geometric terms. Then now this is the first order 4x4 system. Okay. Now capital U we now by the shift called pseudo velocity. Reason by shifting, I want to make this PDE quasi-linear PDE. Okay. Otherwise, the coefficient dependent cosine itself. So this way equation becomes much neat. So we call quasi pseudo velocity. Then for this 4x4 system, there are two eigenvalues coincide. Okay, so the always hyperbolic coincide, but other two eigenvalues depend the speed of the flow speed. Okay, if Q less than bigger than C, this other two arguments also real, so that becomes 4x4 hyperbolic system. On the other hand, if subsonic Q less than C, then you become complex. Okay, so then genetically, this system consists of two transport equations, which really generate complex vortex sheets. Then two non-equation mixed elliptic hyperbolic type. Okay. They actually involve two kind of transition. One transition slow hyperbolic, slow the fixed boundary, degenerate cosonic curve to elliptic. The other part from hyperbolic to elliptic slow transonic shock. Okay. So this is another example. Very naturally, you got the equation, the mixed composite. We call mixed composite. The elliptic hyperbolic type equations. So typical example for that is wide open, like Maha reflection for that, the shock reflection problem. There's those kind of usually before Euler equation. Then outside hyperbolic, then inside this Maha stems elliptic hyperbolic, elliptic one free boundary, another free boundary here. Then the vortex sheets, they also form third free boundary, a three free boundary problem like that for trying to understand Maha reflection. And this problem is still wide open. Light is, so first, of course, the very essential part is what the light space for vorticity function for this Y. Whether this vortex is Kodak, Kodak for that. You can explain this kind of form by BMO function cases. So free boundary for shock we have not better understood. Still, of course, requires further understanding. On the other hand, for vortex sheets is still really quite open. It's still open problems for that, the big open problem for that. Okay, so this I give the first class of the examples of the non-epithelial mixed type elliptic hyperbolic and the related physical several fundamental problems from fluid mechanics. Okay, so I don't know whether we should take 10 minutes break before I move to next topic.
Yes, maybe so we can take a 10-minute break because I can feel that now you need a break. Also, maybe the audience will need some break. So okay. Maybe before we go for a break, let's see if the audience has have any question before we leave. Okay. There any question? Okay. Oh yes, Moonjin. So you can ask the question. Yeah.
Thank you, Chen.
Hi, yeah, hey.
Yeah, good to see you. In the conjecture by Prandtl. So yeah. Is there any threshold or universal constant to distinguish the strength for weak shock and strong shock? I mean, is there any stability issue for moderate the shock with moderate values?
You mean from weak shock to strong shock, or separately? So you mean the transition from weak to strong?
The strong shock means that its strength is arbitrarily large, right? Am I right?
Strong shock does not mean. Oh yeah, sorry about. Yeah, this is a good point. I didn't mention the weak shock means relatively weak. Yeah, this is a good question. Yeah, the excellent question. I talk here here. Weak shock, yeah, very good. Weak shock, I mean, relatively weak compared to strong shock. Actually, stress is arbitrary, quite large. There's limit to the physical problem because you give wedge angle there, maximal limit to the big shock. You give a wedge angle, there are two shocks. One is jump much bigger, other one much smaller, relatively smaller. So we call that one the strong. If jump a bigger one, we call strong shock, and jump a small one called weak shock. But not really assume very sufficient to small shock. Yeah. Reason because you give wedge angle the two solutions, one relatively strong, other relatively weak. So we call this weak and strong. Well, this is a good, excellent point. Yeah, you point out. That's very good. Thank you so much.
Thank you. Thank you so much.
Okay, so maybe now we can take a 10-minute break. So we will resume at 5:21. Okay, so I will see you in 10 minutes.
Thank you. Yeah. Okay. Like how to I make episode? Okay.
Oh, yes, yes. So I think around the end of the first part of a lecture, so I don't know, maybe it's the problem with the signal. So the voice, the sound was a little bit breaking, but now it sounds
So-
okay. So
Oh, the connection. I think the connection. Yeah,
I
probably.
see.
Okay. Okay. So see you. Yeah, I'll come
In
back.
10 minutes. Okay.
Oh, see. Okay. Okay, can you hear me now?
Yes, sounds much better.
Yeah, this wireless though, sometimes connection.
So by the way, did you have a breakfast before giving lecture? It must be very exhausting.
I got my coffee. Okay, yeah.
Oh, I see.
So, Jay, we have an Aux PD cup.
Oh, that's nice. Maybe next time I visit, I will get one.
You should collect one. Yeah.
I should. Maybe could you save one for me for future? Very nice. I see. Yeah. I like that. So have you seen Misha after the pandemic?
He will visit me in 2 weeks. Yeah.
Oh, 2 weeks. Oh, I see.
He will be here 3 weeks or 1 month. Yeah, 3 weeks.
Oh, I see. So please send my regards to him.
Oh yeah. It's well, if you could come in August, he will be here as well.
I see. Yeah, maybe this summer it may be a little bit difficult for me, but maybe some other time.
Yeah. It's depend country by country, you know.
Right.
Yeah, it's traveling.
Right. In Korea, still people are a little bit hesitating to travel international, so we will see. Oh, I see. So now it's actually time to continue for our second part of the lecture. So okay, so now Professor Chen, so could you resume the lecture? Thank you.
Okay. Yeah. Okay. Oh, thank you. Yeah. So now I would like to present the second classes of nonlinear PDL mixed type or elliptic type, or even no type in differential geometry. When I start with now the asymmetric embedding problem in geometry. So we know that you give a surface, then we can define our first fundamental form called metric, right? It's the first fundamental form. Then we want to define curvature, this is the second fundamental forms, right? So this is differential geometry we learned that you want to describe the distance, then in the metric, then you want to see how the surface twist or what kind of motion then related to the curvature. Now the problem is opposite now, like inverse problem. So you mathematically you give a GID or certain property of curvature in various different problems and applications. The question, can you find a surface in R3 or in Rn in Euclid space in the Euclid world with this metric and corresponding curvature? So problem looks very simple, right? The other way around, I give a surface, I compute the second fundamental, first fundamental, second fundamental forms. Then now I question other way around, I give a GID and some property of curvature. Can you find the surface? Right? So it looks very simple, but turns out this problem quite complicated. And in its most, kind of complex, this problem really very important. Okay, the question really, even you could think about who can even more sophisticated surface, right, or sheets can be realized in Euclidean space. So this is a fundamental in differential geometry topology. Then especially in the applications, many applications like understand evolution of the sophisticated shapes of surface of thin sheets in nature. Then the other applications. And now there are many prominent geometers and geometry analysts working on this problem, because this problem really is fundamental and easy to state. Now, in its most general form, unfortunately, this problem has been still open. Okay, so this is what is the reason why, I want to present you. One of underlying reason is because this problem involves nonlinear PDE of mixed elliptic hyperbolic type. Okay, I want to show you. Now, one theorem I want to mention the Nash. He proves the following theorem in 1956, that any n-dimensional Riemannian manifold can be CK asymmetrically embedded in Euclidean space if dimension high enough. So it means that the target dimension n is large enough, then this can be done. Okay, so this roughly is Nash's theorem. So he proves that actually n up to, now is n called generative dimension, this is optimal dimension. This is what the really application we want. But he proves that if target dimension is C is n plus 4 in compact case, and non-compact a little bigger, the n plus 1 multiply n plus 1, a little bigger than compact case, then he can prove it. So this dimension, reduced dimension, has been done by Gromov and Gozer and others, slow want to reduce the target dimension from bigger n to lower n. Now, important for application really is the optimal dimension in the elasticity, material science, or other areas. We really want optimal dimension. And also, what about rigidity of the asymmetric embedding? Means the asymmetric embedding sequence still limit still asymmetric embedding. Then another lowest target dimension. Other complication is the regularity issue, the optimal or standard regularity. Reason because regularity also very sensitive. In 1966, she gave a counterexample. So no, actually, you cannot find a two-dimensional manifold R3. You cannot find C2 asymmetric embedding generically. Okay, so regularity also part of sensitive issue. Okay, so this is all this complication for that. Now, for constructed asymmetric embedding, for two-dimensional manifold on the R3, the first result is a vial problem by Nilenberg when the Gauss curve which is bigger than 0. So this has been extended to now remove strict positive to bigger than equal 0. Okay. Now this is one case. If Gauss curve which is bigger than 0, another Gauss curve less 0. The first result by Hong in 1993. Now, recently, we developed the framework, the complexical framework. We can go to more general, more regular, less regular asymmetric embedding. I will explain later for this kind of asymmetric embedding problem. Then the problem part hard, even locally, for Chen design case. So the result first by Lin in 1986. He proved that the Gauss curve change sign by near 1 point, but gradient is not 0. Then he constructed local asymmetric embedding locally. If you change sign, then you still can do it. This has been extension, various extensions, recent to work even until more recently. Then high dimension, even less results for that. Okay, for the three-dimensional manifold to map the optimal target space of 6, the result, first you assume n state tensor has length greater than 1. Now this can be extended to linear curvature tensor does not vanish, and then the pole extended even linear tensor vanish, but it's covariantly with not zero. Then you could still construct. And a few years ago, this proof kind of complicated. They use macro-local analysis argument, very sophisticated. So listen, 4 years ago, I joined with Cleland, Slammer, Wang, Yang. We give us new simple proof. Ideas use the Friedrich theorem of symmetric positive system. Equation not hyperbolic, not elliptic, but you still can formulate the translate problem to symmetric positive system. Okay, could handle mixed type, independent of type, this kind of theorem. Then use Nash model, we could prove the short proof for that. Basically use the symmetric positive system the theorem, independent of type more or less. So that was a PD approach with proof is shorter. So this is really so far I could see existence for that. Now mathematically, so this means the matching band are focused on M2 to R3. So you give like open set, then you give a metric a local version. Now I give you a metric GI. You're looking for a map in the R2 plane to map to R3. You keep now the metric, okay, the first fundamental, the metric keep the given metric keep the first fundamental form. You're looking for R the surface, right? We construct the surface R such that dr equal the first fundamental form. In other words, you mean looking for R the surface in R2 surface and mapping this Gij, okay, such that they are linearly independent. So this is one of the way in the one chat you construct the surface in this way. Then related second fundamental form defines this form. You give a normal this in you want to match second fundamental form in some way in some cases. So it defines this form. This normal on the surface, your dn minus dn dot dr, this form second fundamental form. So first fundamental form and second fundamental form. Okay, so what the connection the PDE? One of the PDE here, this very nonlinear PDE, you know, three set of equations, three equation, and can you find the solution, right? So now the latter connections through the fundamental theorem in differential geometry. The question, this theorem tells us the following. So you can construct surface if the first second fundamental form Gij, you're giving your second first fundamental form. You're giving Gij. If second fundamental form satisfy Gauss equation, then you can find the surface. So this is the fundamental theorem of differential geometry. Of course, in stat textbook, this is analytic or C infinity. Okay. It turns out that this theorem can be proved with much weaker version. As long as second fundamental in LP, you don't have to be C infinity analytic. Actually, you can construct surface for that. Now, what is Gauss-Kodazzi equation? Now, it's given second fundamental form are now list scaling L, M, N in this form. Then L, M satisfy this Kodazzi equation. Then Gauss equation means L, N minus M squared your curve, this Gauss curvature. Gauss curvature is given. Christopher symbol is given. You compute gamma ij. So the question unknowns L, M, N. So L, M, N, the second fundamental form you're given the idea, you want to find the second fundamental consistent with that. So it means you solve the problem. Can you find the second fundamental form through Gauss equation? So these three unknown, three equations, if you fix one of them, I fixed, for example, N, then Ln, satisfy 2 by 2 first order equation, right? First order non-PDE, nonlinear PDE here, through that. So this system, unfortunately, genetically is a mixed elliptic hyperbolic type. Depends sign of the curvature. Okay. Now in geometric problem, changing sign is very normal. For example, this is like torus. Okay, the shear or donut surface. This is one side, the Gauss curvature. They say here, this Gauss curvature bigger than 0, other side less than. So you slow on this torus, the Gauss curvature change sign. So very normal mini surface, so there's a mixed Gauss curvature really changes sign. Now from come to PDE point of view, this really we take care of this nonlinear PDE of mixed elliptic hyperbolic. Okay, so this is very nature come out to the type of nonlinear PDE of mixed elliptic type. Now this PDE looks we were doing previous case fluid dynamics. This is very close to similar like fluid dynamics. So a few years ago, I was the Marshall, Lemon, the Wang, we think, well, can we formulate this isometric embedding the fluid dynamic way? Okay, it turns out we found the following fluid dynamic formalism for isometric embedding. If you artificially we introduce the Ln as this quantity like that, the momentum, basic momentum related with the momentum equation, static case. So in this form, rho v square plus p, rho minus rho u v, rho u square plus p, q u square, then we'll find Koda's equation become Belling's law of momentum, Belling's law basically of momentum equations. You localize the two equations like a momentum equation, coupling this lower order term, right? This is Belling's law of momentum. Koda's equation will become Bernoulli law. P pleasure P here. P is the function known by Chaplin ds. In this form, Q squared minus P, you plug in. Then with this formulation, we found with corresponding sonic speed of this form, then exact match with supersonic match to Gauss curvature less than 0, supersonic Gauss curvature bigger than 0, sonic Gauss curvature 0. So this really makes the fluid dynamic form, dynamics for formalism for that. So this really observation really help us to thinking this how handle this problem for mixed elliptic hyperbolic type. So it turns out we introduced a new approach, to handle those kind of the weak continuity and existence of Gauss-Kodaly equation, while weak converging method, the compensity companions related with the one part of competitive companions. So recently, this approach has been applied to various settings, obtained now this kind of result that weak continuity is existence of various Gauss-Kodaly equations for that. So this is for 2x2 case. So we could do that the way for that. Now, what about high dimension? Okay, then high dimension. Now, situation more complicated. Okay, besides Gauss-Kodaly equation, there's a Ricci equation coupling the. This is because two-dimensional matter to us with the Ricci equation become trivial, so we cannot. Now, for high dimension, the Ricci equation become plays a law called the normal bundle coming in. So they're coupling now from Gauss equation, Kodaly equation, and the Ricci equation. So genetically, if dimension high, this system very big system. Okay, it's a very complex system. It's no way to you really want to see whether the system elliptic, hyperbolic, and what kind of type. In genetic, actually, this system has no type, neither purely hyperbolic nor purely elliptic for generally curvature tensor for that. Okay. There's a paper, the Brian Griffiths, Yang, they identify this quite a very complex calculation. They identify some state could be hyperbolic. Okay, in genetic, very complex. So in genetic, there's really no type. Okay, very nature from the geometry for that. So we are thinking of the problem called the weak continuity or rigidity of the system from PD point of view. We first question we will ask, if we have a sequence of solution to this very big system, Gauss-Quadratic Lich system, which is a uniform bound LP. Then if they are uniform bound, if they are weak convergence, then weak limit vector field. The question, does weak limit vector still a solution of Gauss-Quadratic equation for nonlinear PDE? This system very complicated. So traditionally, if normally we will try to lower dimension case, we try to first study type of the system. If elliptic, we get the regularity estimate. APLS, we get the control, high C1 alpha, C alpha estimate, then you pass limit, right? But genetics is because the system really no type. You cannot use classical way to thinking. So it turns out we found out, wow, this system also very complicated. But we found a very beautiful structure called difficult structure of Gauss-Quadratic system. Actually, this system, this original quadratic copy, this the system I like. Actually, we can write difficult. Okay, this is like this is really 4 type difficult. Okay, write carefully. Now, for you look at the PDE equation, Gauss-Quadratic, right hand side R1 to R8, they only involve nonlinear term, only involve 3 type of nonlinear terms, quadratic terms. Then coupling with linear terms. So linear term, of course, uniform bound LP weak convergence, you pass limit. So who part you want to pass limit through this 3 type nonlinear quadratic term, whether this quadratic term weakly continues. If you pass this quadratic term weakly, then you get the weak continuity and the rigidity, okay, of this very big system called Gauss-Quadratic Lich system. It turned out very nice, okay? So because R1 to R8 is only involve quadratic linear. Now, if you LP bounded, then this quadratic part, the LP divided 2 bounded, uniform bounded. Then this compared H minus 1. Okay, so this match to called difficult lemma is following. Maybe I've for the difficult lemma. Difficult lemma is for the by Murat-Tata. State the following: if we have 2 sequences, one is LP, one sequence another LQ, uniform bound LP means weaker then imply weaker continuous LP. Another sequence uniform LQ, weaker continuous LQ. Of course, uniform bound LP LQ imply diverging U in W minus 1 bounded, right? Q of W minus 1, minus 1 P bounded. Q will minus 1 Q bounded. Now, if you ask a little bit more, is diverging not only bounded but compact in the space, a little bit more compact. This is compact. Okay, LP uniform bounded, but diverging Q compact in minus W minus 1 P when W minus Q. Then in the product, 2 vector fields. So in the product, one is LP, one LQ, this L1 uniform bounded. Normally, this weak sequence L1 bounded converges to what? converging to L1 uniform boundary, converging to not necessarily limited L1, could be measured, right? But this theorem tells you if a little bit better compact, then not only the inner product L1 uniform and weaker converges to L1, but even weakly continuous can pass the limit, right? So this is really beautiful lemma. The beautiful observation is, of course, you got pass the limit weakly continuous. Now there are various variation of this lemma in different application, different purpose generalizations. But I just in this talk I will focus simplest case. So now this lemma, we found this lemma match here Gauss-Codazzi Ricci equation perfectly well. Using this equation, quadratic from right hand side can prove each minus one compact. So from left to this differential relation tell you this quadratic form weakly continuous. On the other hand, right hand side only involves this quadratic form, right? Like you pass limit. So this is really beautiful, very beautiful structure, like God giving. One side of the quadratic form, LP bound give you each minus and compact right hand side. Then use the left hand side, you get a weak continuity. Weak continuity, you move to right hand side, pass the nonlinear term on the right hand side, weak continuous. Okay, so this is really beautiful. Main part is the structure. We don't know this equation that's elliptic hyperbolic mixed no type, but you structure to gain that. So this is the advantage of those kind of weak conversion method, independent of type. Okay, when you take those kind of problem. Okay. So this is a local version, just one chat. What about globally? So this can be generalized to the difficult lemma. For example, difficult lemma you can generalize now to the Banach space. A few years I was saying we proved that the main part really difficult to operate. This operator ideas, this operator their orthogonality. That is the whole point. So you observe that we can generalize to general operator. Okay, this ST general operator with adjoint operator this form. Then as long as this two operator has orthogonality, okay, with some kind of regularity here, this matches the basic property. Then we can generally set a whole part to the Banach space. You don't have to be the difficult, there's a differential operator, just general operator. You can prove that this is a path limit in the helper space. There's a Banach, each helper space, absolute Banach space. And then this really is you set up the Banach space, then you can put now to the manifold, then independent of coordinate. Okay, they're not independent chart. So listen, the way generalize that, also even more generalization for more version for applications. So this you immediately get the intrinsic difficult lemma on the Riemann manifold for differential P forms. Then you can get the similar result for those forms. Okay, globally independent of coordinate, then you can pass the limit through that. Okay. So then with this one, then you get the theorem. You could prove that global weak rigidity of Gauss-Codazzi Ricci equation. So statement now before I show you the observation local coordinate, right? Then you can do globally the same result hold. If you sitting fundamental form, a normal bottom LP uniform bounded, then the subsequent converting of the whole manifold, then weak limit is still weak solution of the Gauss-Codazzi equation in the coordinate, the global coordinate. Okay. Globally independent of the local coordinate. Then this prove also no restriction on Riemann curvature and type of PDE. It's basically purely by structure for that. Okay. So this is really nice for PDE point of view. We nonlinear PDE have uniform bounded, where the weak limit still satisfies not the same PDE. In generic, not. Okay, so for this Gauss-Codazzi, we have a rigidity for that. So this is also related to rigidity of isometric immersion for problem here. Okay, So this is a PD point of view. Now for geometry, this you assume now uniform bounded for normal bottoms not very geometric. Okay, PD point of view fine. We are very happy for that. So recently we remove the condition with Tracy Jerome. We prove that we only need to assume second fundamental boundary. Okay, you give a sequence of solutions, the Gauss-Quadratic equation, second fundamental uniform bounded. Then you can, from this sequence, we can find a refined sequence. Generally from the sequence, refined sequence still solution of the Gauss-Quadratic equation, such that when epsilon goes to the refined sequence, weakly converging LP to limit the still satisfied equation, weak solution of Gauss-Quadratic equation. Okay, so we don't have to assume the normal bottom uniform bounded, but then you generally change the refined sequence, but still solution, then you pass limit for that. Okay, so idea basically really use because the Gauss-Quadratic equation globally is the invariance of choice of suitable gauge. So idea is choose suitable gauge to control for connection forms. You're giving a form, second fundamental from normal bottom, then you find the gauge, then control the full norm, then you pass it. Okay, for that. So this is what we have to refine that. Basically, you all use the structure of the equations. Then you really don't have to type the little type of PD for that. Okay, so I think we got the. I show you, yeah, this global continuity of Gauss-Quadratic class of the examples which involve non-PD mixed elliptic hyper no type, and we could prove the global weak continuity without the care of the type of equation with those kind of manifold with low regularity. We found uniform intrinsic approach, independent local coordinate, and such kind of problem of weak continuity and rigidity is a little motivation from the early works like the theorem polyconvexity for nonlinear elasticity by John Ball and others. Then also intrinsic method elasticity and non-linear inequality, CRE and his school. And this also connects with convexity integration and flexibility recently to try and construct high oscillatory isometric embedding, the embeddings. If you regulate much lower, then like H principle, like delay, the other way around. Actually, the theorem now, if regularity of isometric C alpha, okay, then you weakly limit no longer satisfy original or rigidity, no longer be pass the limit uniform bound C alpha, then you cannot pass limit through the weak rigidity of isometric bending or rigidity of those PDEs if weak than LP. Okay. This also now connect with the Yang-Mills equation and the immersions. Really, the gauge idea really motivated by Olympic and the Donuts and other works. You could, ideally you choose gauge for that. Few years ago, I edited a book called Differential Geometry and Continuum Mechanics with Greenfield and Robin Knobs. In that book, actually, we collect more examples from differential geometry and material science, continuum mechanics, involve non-linear mixed elliptic hyperbolic. If you are interested, maybe you could check there from that. So overall, I hope I show you several classes of the examples of non-linear mixed elliptic and hyperbolic type. To solve those problems, we need the new methods and techniques, even for non-linear single type, like degenerate elliptic equation, degenerate hyperbolic equation, degenerate parabolic equation or nonlinear transport equation with the Luff coefficient. This specific example, I show you like a space like compressive vortex sheets with coefficient part of Luff. Okay, the question how to do transport equation with stationary points for the coefficient 0 somewhere. That all require new ideas, new methods, even single type. Of course, the more required of the uniform approach for both elliptic hyperbolic phase. One is the free boundary techniques, try to solve free boundary taking method and techniques to transonic flow or your mixed elliptic hyperbolic problems. Then requires, so new ideas. For example, how to do estimate corner between free boundary or elliptic degenerate fixed boundary, or even not a degenerate fixed boundary. This is a problem with considering we use the structure of the equation. What about genetically, how could I handle those estimates? Still not unclear. For the another boundary Hanaka inequality, how to do that? If we do boundary Hanaka inequality, then we can use like a pillow method to handle free boundary problem and others. So could it be shorter some way to improve? Then I also show you some idea works well, like weak converging method and technique. Then they require the new further development. Then some idea, like Friedrich positive symmetric technique I mentioned in my talk is useful for some case. Then see how further development is a kind of idea. Then the other method like entropy method, energy estimate techniques like kinetic theorem, stochastic method, and mesotheoretic techniques, and approximation method for the viscosity, relaxation method, shock capture method, and so forth. So this all, many of them, works for some special case, some special PDE, but still require really systematic thinking for general PDE or not mixed elliptic hyperbolic, what we could do. So this require really new ideas for new mathematics. Okay, so hopefully I have convinced you nonlinear partial differential equation of mixed type or even no type naturally arising many fundamental problems in various areas like fluid mechanics, differential geometry, and other areas. The solution to these fundamental problems in the area greatly require a deeper understanding of nonlinear PDE of mixed type, special elliptic hyperbolic type, and the further development of new mathematics. So I would like to call your attention during this talk. Probably I should stop here now. Yeah. Thank you very much.
Okay, so I want to thank Professor Chen for his impressive lecture. So I have to say I got goosebumps at the end because you started your lecture with 2 concrete examples, and then somehow from there you made really impressive conclusion. Also, that gave us a kind of the direction on how we have to somehow develop our PD theory in the future, because it's somehow some part of the remark are exactly what I've been thinking recently. Somehow I strongly agree with you that one has to really start investigating more unified approach to study nonlinear PD regardless of the type. So I really got goosebumps, and I definitely will look for your recent result. Okay, so maybe stop talking for myself. Maybe we should we should give the audience an opportunity to ask any questions if there is any.
Well, first, thank you for your comment. Yeah, I'm happy I convinced you.
I have so many questions following up, so we will see if audience also has the same situation. Any question from audience?
Okay, so hi, Gui-Qiang.
Oh, hey. Oh, hi. Gui-Qiang, yeah. Oh, long time. Yeah,
Yes.
thank you. Yeah.
I have a quite a simple question. Once I remember Gelfand asked to study some fundamental solution of a trichotomy operator.
Yes.
So, do you know any progress about that?
Well, there are a lot of works. Those fundamentals are based on the concrete, most results are still based on concrete class of equations. Some class equations, yeah. There are specific equations, yeah. So there are, quite many results, different type of equation. Actually, the Jacobi equation has the simplest form, right? They're generalized forms. Yeah, there are many applications, actually, they are generalized forms. Quite complicated. Maybe I moved down here. Yes, okay, yeah. I'll now choose this simplest form, the X. There are a lot of work is generalized, but general Kx, right? Kx at x goes to 0, like a linear term, right? Linear form. You could be degenerate high power. So there are many works that found a global fundamental solution, those kind of equations. Based on mostly that based application. Then when they use some application, you need that K form, Kx form. Then they study fundamental solution, different kind of fundamental solution. It's they're very it's sometimes very tricky. Actually, quite a complicated fundamental solution.
Okay, so when you know that fundamental solution of this trichotomy type some equation, maybe it would be very helpful to analyze the regularity or the property of the solution near some transition, the shock wave.
Yeah, it's your Jacobi equation. You convolute the data. Yeah, the data for that. Then depend the data. Those you are the boundary. Also, the data set up a problem part tricky, not the deletion problem, not the question problem. Mixed type more tricky. You've got the well postness. So if you set up a problem nicely that matches the well postness, then the fundamental solution, you are generating more globally, right? The information gives you a fundamental solution. After you specify, you go data. If you use the data, then you based on behavior fundamental, so the singularity, then you close near the degenerate line. It's I will see, this is more delicate than simply like people use elliptic hyperbolic or upwards asymptotic double equation, much simpler, because you give your index very essential beta, like this beta is essential index will tell you a little singularity at that point, more clear for that way. In this part, I agree with you, is your separation, but degenerate elliptic hyperbolic much better. More precise somehow can do.
Okay, thank you.
Yeah, this is a good point. Yeah. On the other hand, fundamental solution supposed to contain all information, for you to set up. This is I still remember Petrovsky. He first, in Moscow State, he looked the formula fundamental solution, so many pages. He looked down all terms of a fundamental solution. I was very impressed when I was student. So many pages. He lighted down formula fundamental exactly. Later, I used Mathematica check. His formula all correct. He was by hand, by constructing fundamental solution. Was very impressive, Petrovsky, that time at the fundamental early days. Well, thank you. Yeah.
Okay, so let's see if there is any question from Professor Byun or anybody else from the audience.
Hi, Professor Chen. Yeah.
Oh, hey. Oh,
Yeah.
hi.
Yeah. Just now you mentioned the space for the compressible vortex sheet. So you mean the you are going to find the optimal regularity solution space for the vortex sheet in Markov reflection? Yeah. So I'm
Well, very good point. Yeah, very good question. Yeah.
Yeah.
So yeah, this mentions the problem you mentioned this example right this way. The first starting point, because you want to do iteration, the free boundary is like 3 types. If you solve the problem like 3 free boundary problems, you want to iterate. You have to guess what solution space first, right? Correct solution space. Your iteration eventually close the argument. Iterate like more than one free band, more complicated. You iterate one free band, then into the second free band, third free band. Those kind very common. So you first actually guess what is the light solution space. What the light space for the solution could be. Otherwise, your iteration you could not converging if you start a long space. So this is what my point. We have better understand a shock wave water constitute behavior, at least in the various cases. But vortex, we have no information on this kind of compressed vortex sheets. And what kind of space of functions this would be? This is what my question. When conjecture this still could be Kodak BMO. This idea move from the incompressible to compressible, basically. So whether incompressible, it's still the possible. So if we would understand this, then it help you to think about this kind of more complicated problem involve vorticity waves. Yeah. This is an excellent point, question, and still don't know answer. Still don't know. I just ask a question, open question.
Very much.
Okay, so any other question? See, so now it's almost dinner time in Korea, so everybody's getting hungry, I guess. Also, Professor Chen didn't have a breakfast yet. So, but before we finish, because this is such a wonderful lecture, and then I actually have so many questions, but I will save most of them until the next time, until I actually see you in UK or you come to Korea. So let me ask you one question, maybe for the last time. So at the end of your lecture, so you show us the example of your recent work on this GCL equations, the Gauss-Kodatsky-Ricci equations. So you explained that somehow after a lot of computation, you found this wonderful difficult structure, right? So you somehow express your equation in terms of divergence and also the curve. And then my question is just, how did you actually find this formulation? So will there be, say, I'm just generally wondering if maybe there's any systematic way to realize, whether one can find such a structure from the equation, or is it just by coincidence? Because it seems to me that this is all the starting point of all these surprising results coming afterwards. So.
Yeah, well, this is a good point. Actually, we started not from, I presented this Gauss-Kodatsky-Ricci equation. Actually, we started to Gauss-Kodatsky equation. So this is good point. And the motivation actually from fluid dynamics. We formulated this, in the momentum way. So then we started, because we really, I have more experience in fluid dynamics than geometry. So we did the weak converging method for fluid dynamics. Then we start trying this momentum equation, see how to pass, weak continuity, pass that. So this is this connection fluid dynamic formulas, the observation for 2x2. Then we first work out 2x2. Then they found out, well, then we tried to, high dimension case. Then we found to work out very well. And now, this is purely really by the structure, purely structure. I think underline why working, because when we study more because this is another motive is from the Gadot formulation I mentioned a little bit earlier. This is another motivation from the fluid dimension. You write down the Gauss-Kordasi equation in this form. You also could write in the Gadot form, the another geometric model. That is another motivation from the Kaix. Interesting, you know, another interesting phenomenon. This is here like a Chaplin gas, right? This is up here in the mini geometric problem, like a minimal surface problem. So yeah, this related several geometric problems related with Chaplin type things. So yeah, so far we do really the most those kind of this class of equations. This is from various motivation. So your question more broad or more general that this
so somehow, yeah, I have so maybe I dare to dream that one could actually try this kind of approach just for any given maybe nonlinear PD system, right? And then, you know, maybe reasonable class. So that's my dream, I guess, for the future. So I think this could be just a starting point, whether it works or not in the future, because I'm really wondering there should be some unified approach which works for all PDE. So
yeah, well, in one sense I agree with you. In the other hand, those kind of PDE because so complex, like even you know the manifold two-dimensional R3 is so complex, you know, mixed type. You could not find, so far we haven't found a very good uniform approach, except the weak convergence method. We even, you know, we haven't found really other methods really work very well for even both sides working. So, well, when we study more and more, understand better, so clearly we can do much more classes of this kind of equation of mixed type, and then hopefully, like what you pointed, eventually maybe you will get somewhere. And this, of course, a dream, my dream.
Everybody's dream, I guess.
Mixed, not PDF mixed elliptic type. So this is a long-term dream, somehow long-term project thinking about that. So this is we're still early stage, you know, to collect all different examples, trying to generate new ideas, different type. Eventually, we want to unify some way. I think class of non-PDF mixed type, extend mathematics. Yeah, at the start part.
Thank you. Okay, so let's see if there is any more question from the audience.